Amazing. Thank you. Welcome back, everybody. Welcome back to the second lecture of Introduction to Classical Shadows. I know it's the last lecture of today. I'm very tired. I'm very sure that you're also all very tired. So I will propose the following plan. On the first part of the lecture, we will do multi-qubit measurement channel calculations, which will be mostly on the board. Then we will do a break of 5 minutes. Then we will gauge the energy of the room. And if people are, well, not tired, awake enough to follow a little live coding session, then we will together code an example of the shadow protocol with global Clifford measurements. If we will not have time for that, or I see everybody is super tired, and I'm also super tired, then you can just access the Jupyter notebook where I already pre-coded everything, and my GitHub, which I will show in a few slides how you can access that. Does that sound like a plan? I see nodding. All right, very good. So let's dive into the overview that I built up with you, or that I showed you last lecture in the beginning. Last lecture, we did a basic notation session where we saw that tensor diagrams are very useful. Then we reviewed the Pauli measurement scope on a Bloch sphere, and from that learned what this plane state tomography can do and what it cannot do. Namely, it scales exponential with the number of qubits, meaning that it's not very suitable to learn physical properties from our quantum state with full state tomography. Then we took a step back and we're like, okay, before we calculate expectation values of Pauli's, what is actually happening in these measurements, and then what happens when we average over that. And then we saw that it's actually just the depolarizing channel for the single qubit version, and that we can very easily invert that. This lecture, we will look at multi-qubit measurement channels for the local Clifford measurements and the global Clifford measurements. Then I will briefly explain to you the vector 2 design, which we actually need for the global Clifford measurements calculation. Then we will also invert these channels. I will quickly talk about what I mean by observables, and then I will state, finally, the classical shadow protocol, which, as you remember, is a readout protocol and also an estimation protocol. That's the plan for today, and then we will see and code, and if we don't code, I will show you a video, that our things will converge, but we will pose the question, how do we know that we converge to the right value? And if we did not converge, how far are we away from our true value? This will then be solved in the third lecture. It will be a lecture on complexity bounds. And it will be probability theory, which we then apply to our shadow framework. All right. Any questions for that? No? So just a quick reminder for those who have not been there yesterday. Richard and me pose a challenge to you. Namely, if you do all the calculations that we do here for linear functions in rho, that you could do for quadratic functions in rho, if you do all the calculations, namely define the single shot and the multi-shot estimator, calculate the sample complexity bounds, and also code the protocol, then you can send us your solution together with a little CV and your motivational letter. And then we both will, well, decide on who we will invite to Linz, and all the travel expenses will be covered coming to Linz, staying there for a visit, and then going back again to your university city. The deadline is in 2 weeks. I will show the slide again tomorrow, and I will not change this in 2 weeks. Yes. Yeah. 2 weeks starting tomorrow. Because I will show the slide again tomorrow, so it's 2 weeks from tomorrow. Yes. All right. And I also now, because I was like, I want to have a little collection of material and the collection of the question, and the Slido poll didn't really let me let these things open. So I just decided on opening this online pads where you can just, as a participant, write in whatever you want in a participative live online way. And the first part that you see there is a collection of links. And then I also copied the questions from the last Q&A session in there because I think they're very good questions. And I hope that after the third lecture, I can answer all of these questions all at once again. So if you have questions, please write them in there. And also you can see a link to the GitHub, to my GitHub where I uploaded the Jupyter notebook. So I hope everybody scanned this code. Yes, so this is the pad. And, oh wow, 30 participants, exactly. And I think you all have like another color and everything. And you can write in there and, oh, cute, people did stuff. And then there's the last Slido poll from yesterday. I think it's still open. So if somebody, okay, can everybody raise their hand who was not there yesterday during the first lecture? You were not there. And you were also not there. Okay. Okay, maybe I will not reopen the poll for 2 people, sorry. Wait, yeah, okay. And then also the paper that this whole lecture is based on is this Predicting Many Properties from 2020, I think. Here's the archive link. Then this is the GitHub repository to this lecture now that I just recently, 2 hours ago, created. And I also uploaded the slides there. I know that I can also upload them on the webpage of the conference of the summer school, but now I didn't know who to write that. So for now, if somebody needs it for now, you can download them here. And then you can also see here the tutorial/result is the tutorial with the results that we will today code together. And this is the empty one. Okay. And then a little bit of shameless advertisement for a repo that I created. And I think it's pretty cool. I wanted to show you quickly. Is a repo where you can draw your own quantum circuits and they look hand-drawn. And I just opened that. Like if you click either on this link when you want the right to left direction or this link for the left to right direction, then you will end up in a draw.io interface where now it was kind of didn't work. Oop. Okay, I don't know why it doesn't work. Normally it opens, here we go. You have cute little diagrams that you can click together and then make your own circuits very quickly, like this. And then you can also give it names. I think I need to do mathematical typesetting. This is a Hadamard code. Yeah, and like this you can just quickly put together circuits, and I think it's cute. And Richard actually used that for his lecture notes, and I was very proud to see that it works very well. Yeah, anyway, just a little bit of advertisement. This is also in here, but the most important thing is that this GitHub is now public. Okay. Next slide. Phew. Okay, let's dive right in. I hope you remember this table. And the goal of this 3 lectures is to fill in this table. And then now it's a little bit overwhelming, but hey, we already filled in 2 things. And the general direction is down, right? So we first calculated what our measurement channel is given a certain measurement ensemble. Then we calculated that this is just the deprocessing channel. In this case, we know how to invert that. It's not a physical channel anymore. Then from this, we can define our single snapshots. And then in the 3rd lecture, we will calculate the variance and the sample complexity of these things. And now I want to do this with you, so the global Cliffords. But before that, I just want to quickly recap what this measurement channel is, because I think last time the most confusing concept was this measurement channel. So I wanted to approach it a little bit unmathematical, and the only things that I could formulate is the sentence. So the measurement channel is the sum over all possible post-measurement states weighted by their probability of appearing. So if I have a quantum state and I just measure this all, like infinity times, and in our example we had the measuring only in the z basis, then I know that if I look at this collapsed measurement state and I average over all these collapsed measurement states, I know that this is the same as just forgetting about my diagonal terms and just being left with the, forgetting about the off-diagonal terms and being left with the diagonal term. And then we took together 3 projective measurement sets, projective Z and then X and then Y. And then us humans have to decide that we want to measure 1/3 of the time in the Z projective measurement scheme, 1/3 of the time in the X, and 1/3 of the time in the Z one. No, you know, X, Y, and Z. And then we get this funny sum over, well, bond probabilities that weight their respective post-measurement state. And we derived that this is the same as depolarizing our quantum state with the depolarizing parameter of 1/3. And now if we would just write this out, it looks very funny, no? Like this is the post-measurement state. If we would do this infinity many times with this measurement here. Okay, so this is the measurement channel for the single qubit case. And now we go to the global Clifford measurement channel. So our measurement ensemble is not just the local Paulis that we measure, but kind of global. It's a global measurement ensemble. That's why this U is now stretched over the whole, over all the qubits of my psi. Yes, and we want to now calculate this thing here. And I will do this on the blackboard. And please, again, if you have questions, interrupt me. I will go extra slow because, again, we're all tired. So, global Clifford measurement channel. Global Cliffords. I will just copy the equation here. M rho is the same as 1 over how many Clifford unitaries there are in our Clifford group. I actually don't know that number. I think it's double exponential or something, but you will see in the end we don't care what this number is. We just care that it is the cardinality of our set of global Clifford measurements. And then we sum over the unitaries in my global Clifford measurements. And we need to also sum over the bit strings that we could get out. And then we have the bond probability times the post-measurement state. That doesn't really change from the local case. And how you can interpret this is we sum actually over all the columns of all the global Clifford operators. Now we do the same trick as we did yesterday twice. So we imagine that there's an identity here. We pull in this thing inside our trace with a tensor product. Then we need to make sure that we take the trace only over the first subsystem. And because the trace is linear, we can just insert the sum inside the trace. All right, do you remember that? Yes, very good. Okay, so this is trace 1, so only the first subsystem. Now we have a huge sum, brackets, sum over, I will not write that out, I think you know what that means. And then we have U dagger B, B, U. We have this twice, so on 2 tensor spaces, and then we shall not forget row tensor, and then an identity that actually, right, is n many single qubit identities. So I write that as this, and we need to close this bracket and then this bracket. This looks familiar, right? We had the same for the local Clifford measurement. And now, what is this thing here? And last time I cheated a bit. I just calculated it by hand Well, my computer did that actually for me. And we saw that this is the identity plus the swap operator. Now I cannot code that anymore or calculate by hand anymore, because already the 2-qubit Clifford group has like 11,000 elements. So it would be possible, but I cannot scale this up to an arbitrary n. What do I do? And I already told you that the Clifford measurements where we have these autoproducts B cutting out the columns, is a vector 3 design, because Clifford unitaries are unitary 3 design. And I want to just briefly explain to you what that means. That looks a bit scary. I will first explain you this equation. We will go to a very easy example, and then I will show you this equation again. But a vector 2 design is generally defined as we have a finite vector set. It also goes with integrals, but in this case, we have a finite vector set, meaning that we sum over them. We need to divide the sum with how many vectors we have in our vector set. And then we take the sum over their tensor power to the tensor product of t. And then if this is a vector 2 design, we know that this has a very particular result, namely some prefactor that depends on the dimension where our vectors live in. T is the moment that we look at. And then we have this sum over operators. And maybe you were in the lecture of Martin today, but he actually also talked about permutations. So these are actually permutations over my subspaces, and these are permutation of my T subspaces. So the swap when pi would be 2, 1, for example, would mean that you swap, So I always write this P as something like, I have my, if T would be 3, I have my subsystem 1, 2, 3, and then it can swap this to 1, 2, 3 again. Or another permutation would be I have 1, 2, 3, and then this could be swapped to 3, 2, 2, 3, 1 or something. So it's all this combination of permutations that you can write down here. And in the t equals 2 case, we only have 2 permutations, the identity, so we don't permute anything, or we just swap the 2 subsystems. And this is exactly what we had for the single qubit case, right? Identity plus swap. And this is the reason why we saw that, because it's at least a vector 2 design. But in general, you can generalize this to any finite set that is a T design. Okay, I always find that a bit counterintuitive, so let's start with an example, because scalars we know very well how to deal with, right? Vectors are like, it's like a object with many numbers in it, and I don't know, it has some norms and everything, but scalars we know how to handle. And in the scalar case, our uniform distribution between the 0 in the interval 0 and 1 is something that we're very familiar with, right? We just sample randomly between the interval 0 and 1 and just get a number out of that. And this is the uniform distribution over this interval, which I would denote as x sampling from the 0.1, 0 and 1 interval. And now we can calculate moments of this distribution. And with moments, I mean something like the expected value of, and then the random variable to the power of k for the kth moment. If k is 1, then we have the expected value of x. And in this case, it's 1/2, right? If we sample a million times and then average over that, we will get 1/2. First moment. Second moment, does anybody know what the second moment is? So expected value of x squared. 0 by what? 68, right. 1 over, I had 1 over d, e, 1 over e. No, almost. It's 1 over 3. But I like the word. Okay. And in general, here you can calculate, because it's very easy. It's just an integral over, integral over dx and then x to the power of k. So then you can solve this integral and then whatever. So this is the equation for the kth moment of our uniform distribution. And if I now take another distribution, I want to compare it to this distribution, how do I compare to random distributions? I don't know. I cannot sample infinite times and then say, are you always the same sample because there's randomness? Like, how do you compare them? And one way of comparing two distributions is looking at their moments. For example, I have a very easy distribution. With the probability of 1/2, I get a 0, and with probability of 1/2, I get a 1. What is the first moment of that? 1/2, 0.5, very good. Yes, it's 0.5, right? I do expected value is I take 1/2 times 0 plus 1/2 times 1. That's 1/2. Okay. What's the second moment? Sorry? 1/2 as well. Very good. So we see that the first moment they match, but in the second moment they're not the same anymore. Meaning that this is actually a, well, one design when we compare to the uniform distribution. Now, yesterday I played a bit around with it and thought, can I design a distribution that is discrete only with two values that also is similar to the second moment? And yes, you can. It looks like this. Because then the first moment is 1/2, the second moment is 1/3, but then in the third moment it didn't work anymore. All right, so that's how you compare probability distributions with this moment. And we do the same with vectors. And if we do the same with vectors, then it looks like that. That's the whole story. And if we now look at this and say, what is the uniform distribution here? Because now I compared everything to the uniform distribution. For vectors and unitaries, it's called the Haar distribution. Doesn't matter so much, so only that you heard that. That's like the uniform distribution for my vectors or for my operators. Okay, any questions? Yes? The KL divergence? Sure, you could do that. I mean, then you can also calculate how far away two distributions are. Yes. It's not that operational, you know, like you just calculate this e to the power, yeah, KL distance, I forgot logarithms of things. Yes, you can also do that. Okay. Good, so we can use that because we know that, or I tell you that all the columns in our Clifford unitaries actually form a vector, at least a vector 2 design. So we can just use that. We just need to figure out these prefactors, but let me tell you, that's quite easy. So how many elements do I have in my vector set when I look at all the columns of my Clifford operators? Nobody? So I have how many Clifford operators I have times the number of columns that we have, right? So 2 to the power of n. That's the vector set that we're talking about here. Good, so this prefactor we figured out. This is actually what we have here. And now we need to go to the right side. We want to know what is it actually. So this is the binomial coefficient here. Just to remind you, n over k is the same as n factorial divided by n minus k factorial, k factorial. And if I now insert that t equals 2, I can calculate the binomial coefficients of d plus t minus 1 is d plus 1, and then over 2, inverse of this, and then times 1 over 2 factorial is 2. And now we can calculate that. That's just, I want to shall not forget the inverse. So I have d plus 1 factorial divided by, and now d plus 1 minus 2 is d minus 1 times 2 factorial. And I can rewrite this thing up here as d plus 1 times d minus 1 times d minus 2 times d minus 3. So this is d minus 1 factorial. And we can now see that this just cancels out. Yeah? So this is bloop, loop, and we only are left with this in the thing, and we cannot forget this over 2. Now I will take the inverse of this fraction, so this goes up, so the 2 goes up, there's nothing left, and this goes down, so this goes down, d plus 1 times d, and then I have times 1/2, which cancels. So I have d plus 1 over d. This is my prefactor here. And we know that our d is the dimension of our space that our vectors live in, and for the global Cliffords, that's 2 to the power of n. Every vector that we talk about has length 2 to the power of n, so I can write 1 over 2 to the power of n plus 1 times 2 to the power of n. Good. We calculated these prefactors, and now inserting them, I need so many boards today. So we have 1 over how many elements we have in our vector sets. Clifford group times 1 over n. Then we have the sum over my Clifford group, all my bit strings, u dagger b u equals the prefactor 1 to the power of n, and then we have, because t equals 2, we have 2 terms in our sum. We have the identity and then the swapping my 2 vector spaces because t equals 2. I will show you how this will look like. So this is my identity, which I now define on, which has the dimension 2 over n, and then plus swap. That swaps my 2 tensor spaces, but my 2 to the power of n tensor spaces. Okay. And now we can see that we can just cancel this factor here, and we are left with the term that we actually wanted to calculate. Whoop, whoop. So instead of there, what I pulled in, is the sum over my vectors, I can just insert this right-hand side. So this one is the one on the right. So I can write trace 1 of my swap. And now I need to be a bit careful, like this is on 2 to the power of n, and then I don't know how to write that properly. And the 2 acting on row. No, I'm really messing up notations. 2n. Okay. And I forgot the prefactor. 1 over plus 1. Is everybody with me? Yes, I see nodding. Very good. Now, what is this object here? Because yesterday it was easy. We just talked about, 2-dimensional vectors and everything. What is this here? And the swap operator here, that I have put away, is now defined on n many qubits. So I have n of these lines here, each representing a qubit, and then it acts on, this tensor itself. So these are n qubits here, or n lines, and then I have here again n lines. And this in itself would be now this identity here. Identity tensor 2n would be now only this lines. But what the swap is doing is, I told you it swaps this whole thing with this whole thing. And that means that it swaps this with this. So this is the first of the second one, then this with this, and so on. And then this with this, whoop. And then also the second one up. So here, this, second one, and then like this. Yeah? I think yesterday somebody asked, how can we generalize from single qubit to multi-qubit operators in this diagram like this? So the swap is really just swapping the upper with the lower one. And we know that here we have two terms, right? So we have swap acting on rho tensor identity. And I will just, because I don't want to draw it so many times, what that means is we have rho on the first subspace. So here is rho, which can be highly entangled. I'm not assuming any separability here. And then this rho is tensor n times identity. So I just extend these lines here. And now we take the trace over the first subsystem, and I was not very specific here because 1 means actually only the first tensor system. What I should have written is 1 to n. So this partial trace here means taking the trace over all first n subsystems. Let's do that. First one. Second one. All of that in between. And 1. And now we can do the same trick as yesterday. I can see that this leg here, it points to the right side, and I can just retract it, loop, 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 until here, and just pull it back. It will not change anything. And I can do this for all n legs. This one is also connected to the second one. And so on. So this is rho. Okay, so the first term of my sum is swap acting on rho tensor identity. That's just rho. And the second term is identity times rho tensor identity. Taking the first trace, only traces out rho and leaves my identity intact. So, I don't have space. I will just write here. This is 1 over 2 to the power of n plus 1. Can you see? Okay. Times rho plus trace of rho times identity times, and that's it. And now we can do the same trick as yesterday, and I don't have space to do that. Yeah. Okay, so I go from here to here. So my m of rho is 1 rho plus 1 over this one trace of rho identity. I extend this part by the dimension of my Hilbert space like this. And now we see that this is actually 1 minus 2 to the power of n plus 1. And if we call this P now, this our P, this our P, we derived that this is also the depolarizing channel, but with a very, very small depolarizing strength acting on rho. Ta-da! We did it. So, we use that. Our measurement channel is actually the depolarizing channel, a global depolarizing channel with the strength 1 over 2 to the power of n plus 1. Very good. Any questions? Yes. Yeah, we know, we assume we know. I mean, probably somebody in this room can prove it. I'm looking at you, Richard, that the Clifford operators themselves form a unitary 3 design. And this also means, and you can also show that they form a vector. Like if you now take all the columns, they form a vector 3 design. And this always implies that they also form lower designs. But I assumed that the Clifford unitaries form a vector 3 design. Yeah. I would not even know how to prove that. But yeah, good question. 10 years ago. Good. Good. So we filled 2 more tiles. Whoop, whoop. Now we come to the, yeah. Mm-hmm. Yeah. Very good question. So I always used only these 3 unitaries when I looked into single qubit gates, right? Because I showed you this huge table of Cliffords, and then I said, oh, if I like all these rows stabilize my Z, or map Z to Z, Z to X, or Z to Y, so we can just use the upper row. And I never really mentioned it, but it does not matter in these calculations. It doesn't matter if we just use these 3 ones or if we use all 24 Cliffords. We will get the same result. Probably, because for 1 qubit we can. Probably for the upper one we can also throw some away, but I don't know how and if. But I think so. That's a good thought. Maybe you can work it out. Okay. Thanks for these contributions. Good. Now there's a gap in the middle, and we will do this now. Also an n-qubit measurement scheme, but instead of global Cliffords, we only do local Cliffords on every qubit. And now we need to work out what this measurement channel is. And this requires now, and it's a bit of an involved, not complicated, but a bit of an involved calculation. And I find it super useful to know all these techniques and how to use them. So I will go through it with you, even though maybe in the end you say, oh, that was actually boring, that was super trivial. We probably need more than 2 boards. Alrighty, I will copy this equation. Okay, we have our unitaries now in this n-fold group of unitaries. Now our bit strings are again, as before, bit strings as length n. Now this should look very familiar to you. Jadwiga B, B, U, rho times the post-measurement state, U. Okay, and we will now use tricks to make this easier. First of all, this quantum state here can be global. Even though we have local measurements, our quantum state can be global. So we need to make a trick. We need to use a trick to also make it seem local. And for this, we will use the Pauli decomposition that we used yesterday. So use every quantum state rho can be decomposed as a sum over the n-fold Pauli group, where the trace, the overlap of rho and p, weights the Pauli itself. And this Pauli here is a local operator, or not a local, it's separable operator. So this Pauli here actually I can write as j equals 1 until n, and then pj. Okay. Now we can insert this in here. So instead of rho, we write this sum here. 1/3. And I will pull out this factor already because I can, because of linearity, already pull it out. So then we have the sum over u, then all my bit strings. And now we have the sum over all the Paulis. Another bracket. And now Jadwiga B, B, U. I know it's a bit boring, but just keep with me a bit. All right. Now we can use what I just wrote here, and we can use something else, namely that this Jadwiga B, B, U is actually just local unitaries and local cat vectors. So this is Jadwiga Bj, Bj, U. Good. So we can insert that here, and we can also insert that here. And then I will also take the liberty, so then we will also insert that here, and I will also take out the sum together with this single number here, which I can everything just pull out here. A lot of things happening here. If I'm too fast, please tell me, or if I'm too slow. So we have 1/n, sum over our measurement ensemble. Now the sum over the Paulis, well, Pn, trace of row P, and now comes, because right, this is just a number, I can pull it out here, and now comes trace of the tensor product of my columns of my local Cliffords, and then tensor. So this is actually tensor of Pj closing, and now here too, tensor product Jadwiga J. I forgot the J's. Nobody's saying anything. J, J, Bj, Bj, U. Phew. Okay. A lot of J's flying around. PJs, UJs, BJs, everything. And we will use now some properties of some properties of our tensor product. So if I have what is that? Here, how do I write that? I have A tensor B times C tensor D. This means that I can just calculate the products in the respective tensor space. So this would be A C tensor B D. So we can use this to kind of scrap this tensor product here. Doesn't matter. So we will kind of scrap this and then assume that there's a times in between this and this operator. And then the second thing that we will use is that the trace of A tensor B is actually trace of A times trace of B. So the tensor product in the trace becomes a times outside of the trace. And because everything in here is just separable, we can just pull out this tensor product out of the trace, and then it becomes a product. Magic. Good. So we use these things now to write this. Well, all my sums. I will not write them out anymore. You know what, and P. And now we have our product over all our qubits, trace of Jadwiga J, BJ, BJ, UJ, PJ, times our tensor product. I think lots of people voted more blackboard proofs. I hope that satisfies your need. Did I make a mistake? I saw somebody squinting. No? Okay. Phew. Good. That still looks complicated. But we can use something else. Namely that for each scalar A, alpha, we can just swap around the scalar in our tensor product, and it does not matter. So alpha times A tensor B is the same as alpha tensor A tensor alpha times B, the same as alpha A tensor B. And here we have just numbers. This is just a product of numbers. And here we have a tensor product structure. So we can just pull in this whole product here and then let this tensor product take care of our product of our jth qubits factor. So this is the same as always copying these factors here. U, B, P. And now I pull this in. So now we have a huge trace of j equals 1 until n, Jadwiga, BJ, J, P, J. This is our number from the product, and then we need the operator. And this looks a little bit familiar, no? It's like the weight of the one probability with some factors times the operator itself. Now we just need to somehow make sure that we get the sum in here. But that's easy, because in this case, the sum of our products is actually the product of these sums. So we will use that. I told you I will run out of space. I will write it here. So we will use that A plus B. So this is like a sum, and then times another sum is the same as the sum over the product. So AC plus AD plus BC plus BD. Right, so right now we have this. No, right now we have this case. The sum is kind of outside, and then we're summing over the products, but we can just also pull it in and then kind of make sure that the sum is in this right space that it acts on. I think I need to write there. And this is a bit distracting, no? Oh. Do you have questions until here? No? Then you have 20 seconds to relax your brain. Where's the wipe? Here. When did we start? At 4:30? Very late, no? Wow. Okay. So no coding today, probably. Okay. So we are done there. And I just told you that, well, now it's bad that I did not write out these two sums. But the sum over the u and the b, I can just pull in here. And then I need to keep track of the index. So, okay. Remind me that I need to pull in the 1/3 too. So our Paulis stay outside. They actually are responsible for this whole trig, rho p. And now I have my huge tensor product here. Okay, huge tensor product. And I will write this 1/3 in here, which is fine because we have this n times, right? Right, 1/3 to the power of n is the same as just putting it in front of this tensor product. And then I have my sum over, now it comes uj in the single set and bj in my bits of length 1. And the trace of Jadwiga, and now we need to keep track of these qubit indices. It's important. Pj times Jadwiga bj u. Wow, I really estimated the location of the bracket correctly. Okay, do you believe me that we can go from bottom right to this? Richard believes me. Very good, you believe in me. Okay, good. Because Richard believes in me, I think everybody believes me. So this is now something that we know, right? This is a channel that is the single qubit measurement channel. And we know, and I should have put it on the slides, but we know that this is actually depolarizing with a strength of 1/3. And now we need to take care of, this is not rho, but a Pauli, doesn't matter, right? So this acts on my Pauli Pj. I know you were not here yesterday, but we proved that yesterday. Okay, so we need to, like there we expanded everything and now we need to kind of pull everything back. So this is the sum over p and rho p tensor j is 1 to n, the depolarizing channel strength 1/3 of my pj. Good. Now we can pull everything back in because it's linear. This channel is a linear function. We can pull in this thing, and then we can actually pull in just everything. So in the end, this is until n of, again, big bracket, n, trace of rho p, and then we have the tensor product over our pj's, which is just our p, and who recognizes this expression in the depolarizing channel? I see nodding. Okay, you recognize it. Can you also tell me what it is? No? Just look on the right bar. I think in the very top, the second line, that's how we decompose our rho, right? So we can just literally say, this is our rho. So this is just the tensor product. Wait. I need to, sorry, I made a mistake. I forgot that this is now the tensor product of depolarizing channels that act on this whole space. So this is just my n-fold channel. Okay, maybe that's why you were confused. Sorry. Acting on rho. Okay. Pew. And it makes sense now. Like, we make local measurements. So actually what we do is we locally depolarize everything. So our measurement channel is just the tensor product of n many depolarizing channels with strength 1/3. Good, you made it. That was, I think, the most heavy calculation this lecture. Maybe even of next lecture. Okay, very good. So now we filled in our measurement channels. And now it will be very easy to define our snapshots, because I told you that we use the inverse of the measurement channel. That was the heavy lifting. So we now look into our snapshots. And one of the core results of this paper that I told you about is that you can really think of every single tuple of measurement or rotation that you applied, and then this one bit string that you got out from the projective measurement. This one data tuple is one shadow of your quantum state. So already just doing one projective measurement in a certain basis gives you one shadow. And given this shadow, you can construct this snapshot, what Elena always calls it, and I overtook that term. This is the snapshot of our quantum state. If we now apply the inverse of our measurement channel to this post-measurement state that we got out. And for just because we will use this, right? So we have in our single qubit case, our inverse of our measurement channel is the depolarizing channel with strength 3. And if we now just insert this outer product, so our post-measurement state, inside of here, then you will see that this is 3 times the outer product, and then 1 minus 3 is minus 2 divided by n is 2, so minus 1 identity. That's our single snapshot that we built from a single classical shadow. For the multi-qubit case, we have this tensor product structure of all these post-measurement states on our single qubits. And for the multi-qubit case with global Cliffords, you remember we have this 1 over 2 to the power of n plus 1, so we need to invert this. So it's really just 2 to the power of n plus 1, the post-measurement state minus identity. That's it. That's how we define our snapshots. And now why do we do that? Like, okay, it looks cute and it's kind of pretty, but why do we do that? To fill in the table? No, I'm joking. Because now we can look at the classical shadow protocol and what this protocol actually is. So this is now a little bit the heart of this lecture. This is one of the most important slides here that you will see. And I just told you that you can define this single shadow, and then you can define the snapshot. And I tell you that if you now do this a lot of times, so n many times you draw a random measurement basis, be it local or global, then you get out your predictive measurement outcome, your outcomes, and then you always sum over these snapshots that I told you, that when going, oh, not t to n, sorry, that's a typo. That's not capital T, but that's capital N, to infinity, then we will recover our quantum state, rho. And now you can be like, wait, but we didn't want that. We didn't want to do quantum state tomography. Why do you tell me that we can do quantum state tomography with that? Well, it's important that we make sure that this is the case. So in theory, you can do quantum state tomography with shadows. And if you do infinite many shots, then you will recover your quantum state. And this is important because if this would not be the case, why should we do that? And I will just quickly show you why the expected value of our snapshot is actually rho. So what we can write is the expected value of rho hat is the same as the expected value of the inverse of the identity channel of U Jadwiga B U. And this expected value now goes again over all of these U's and B's, right? And because this is a linear function, we can pull it in of U Jadwiga B, B, U. And this here is actually our measurement channel acting on rho. Because we are averaging over all the possible post-measurement states. This is our measurement channel, how I defined it in the beginning. So what we have written here is the inverse of my measurement channel acting on something where my measurement channel is acting on, so this is rho. Good. So except of that typo, this equation there is right. So what do we do with this now? We know that, yes. I think it's always linear. Yeah. Because it's really just the expected value of all your possible post-measurement states. Well, we need tomographical completeness for that, maybe. This only is true when your measurement can actually resolve all the degrees of freedom, or your measurement channel has full rank, so that we can invert it. But yeah, not sure. Probably. It's always linear. Okay, it's always linear. Okay, so what do we do with that now? We could do state estimation, so quantum state tomography. I told you we should not, but let's just go through the example that we do that. So then we have, and now I will just introduce some terms that I normally use with probability theory. So we have a single shot estimator, this one snapshot. We can average over the single shot estimator, and the randomness comes from two places here. We have to choose a measurement basis, and then the quantum state chooses for us what measurements we get out, what outcomes we get out. So if we now sum over this, then we have a multi-shot estimator, which we always denote with the bar over it. And then in expectation, so when we just do this a lot of times, so and to infinity, we should get our rho. This is the expected value. And again, I told you we should not do that with tomography. So what should we do with it? And the most prominent thing that you should do with it is estimate linear functions, so observables. And here we define our single shot estimator as trace of the observable that we want to look at with a snapshot. Then our multi-shot estimator is just this averaged over n many rounds. And because we just showed that our expected value of rho hat is rho, we can do the same calculation here, and we see that in expectation, so n to infinity, we will always recover trace of all rho. And with that, we come to our classical shadow figure that I wrote down for you with local measurements. So the protocol of classical shadow is as following. You prepare your quantum state, rho, well, in this case, it's a vector, so psi, but whatever. You apply your layer of random measurements, and then you measure your outcome. Then, starting with the first snapshot that you get, you can build your first shadow that you get, you can build your snapshot, and then, in a parallel way, estimate all of the observables that you want to estimate. Because here I never said that you can only estimate one observable. You can do this for as many observables as you want to with the same shadow. And then, because this is a sequential protocol, and we just destroyed our rho, we need to prepare it again, apply a random measurement layer, and measure. Then we send our data tuple to some HPC center, and it does its thing. And the quantum computer, again, prepare rho, measurement layer, predictive measurement, and so on. So this is the shadow protocol, the sequential readout protocol that I talked from the very beginning with you, and we just derived the theory. Good. Now, what observables do we look at? I never said what observables. So first of all, an observable is just defined on its actually linear function on our Hilbert space, which is, well, in the Morse case, Hermitian. And then we write our linear function in rho as trace of our rho, not telling anything new to you. But in the next lecture, we will see that it is very nice to think about traceless observables. It makes our life much easier. And why can we do that? Given any observable, we can always make it traceless. And it's just a kind of a concatenation, because we just take this minus the trace of all divided by how big the diagonal of our identity is times identity. And you can see that if you now calculate trace of this O, you will always get 0 by just rescaling it. So it's really useful to think about only traceless observables. Fortunately, all our Pauli observables, except if the identity is traceless. And then also, it's very good to think about k local observables. And this means that if we have an observable that has n minus k many identities in this string, how we can write it, and then the rest, so k many things, is just an observable that we can, just expand in our space, then this is a k local observable. If we look at the Pauli string x tensor identity, this would be a one local observable. Okay. I hope I'm not telling you anything new. This is just how you define k local observables. And in our case, we will always look at a lot of local observables. For example, xx and xy and xz and everything. This will be then many observables that we can look at the same time in our classical shadow protocol. Good. Now, I also want to feature a thing that I find really cool with classical shadows, because right now we define the snapshot and look like the matrix, right? So we always think, oh, we need to always estimate things with a matrix. It will become big because the snapshot is kind of big, but we don't need to do that. And one neat little thing, that I want to look at is this expression here. Row hat is a matrix, z is a matrix, trace over that is a number. So why should we write down our snapshot as a matrix if we can, well, look at numbers? And here are some computer scientists, right? Like, it's always nice to have numbers instead of big matrices. So I just want to quickly show you a calculation that will be, well, a bit trivial once you see it. So trace of row hat z in the single qubit case is the same as trace of, now we need to insert row hat 3 Jadwiga b u minus identity times z. This has two terms, 3 times Jadwiga b u minus trace of z times identity. And we know that Paulis are traceless, so this is just 0. Loop, 0. So what is this? Ah, I forgot a z. What is this term here? It's still a matrix, right? But what I always like to do is like to rewrite these outer products of bits. And I can do that by looking at it a bit carefully. So if the bit is 0, then this matrix is this. And if my bit is 1, then this matrix is this. And the upper part looks like I can just do identity plus z divided by 2, right? Identity is 1, 1, z is 1 minus 1. So I can just recover this, and this is actually identity minus z divided by 2, because this minus makes the minus in the upper right corner plus, and then it kills this one. I think, okay. So you see that it only differs in the sign. So you can just write it as identity plus minus 1 to the power of the bit that you got times z. And now we will insert this. Jadwiga, now we have this thing, 1/2 identity plus minus 1 to the power of bz. Z. No, I forgot my u's. Right? No, it's here. I'm getting tired. 1/2 this, and then my u, and then my z. Okay. Again, we have two terms here. 3 times trace of Jadwiga. I pull out this 1/2. Jadwiga identity u z plus 3/2. So now we take the second part. Trace of Jadwiga Z, U, Z. I forgot my B. Okay. I'm sorry, I'm a bit tired, so maybe I made mistakes. Okay, good. This is identity, Jadwiga U is identity, trace of Z is 0, so this is 0. And the second part is now 3 minus 1 to the power of B divided by 2. And this expression here, I already see that if my Jadwiga U is identity, then I have trace ZZ. Z times Z is identity, so I would have trace of identity here. With every other U, I get another Pauli here. And a Pauli times a Pauli is another Pauli. So this will always be 0. And it will always be 2. It will only be 2 if this is identity, if these U's are identity. So this is a delta U being identity, which means this is 1 if U is identity, and it's 0 if U is not identity, times trace of identity, which is 2. So we can cross this away. So our single shot estimator, without having to touch any matrices, is actually 3 times minus 1 to the power of B delta my U has to be identity. And now you tell me, like, of course, like, if my snapshot was taken in the Z basis, and I want to measure in the X basis, and I want to measure in the Z observable, then I will always get garbage. It's always 1/2. I never get any information in the X basis for my Z estimation, right? But okay, now you have seen it in that this is actually the case. And that means that we can now, this is just a small example, but if you know your observable that you want to look at, you can actually just write down numbers. You never need to fully reconstruct the snapshot and then sum over the snapshot, and then with this sum over the snapshot estimate any observables. You can always, if you're smart and you know things about your observable, you can always break it down to a number that only takes in what did I measure and what did I get out. Okay. I find that neat. It's cool. And it really makes calculations in the classical post-processing much easier. Another thing is that we can do the same thing for, if you look at Pauli correlations. So I want to now calculate Z tensor Z. And then you can do the whole calculation again, and you will get out that these are your single shot estimators. Again, you do not need to reconstruct any matrix here. Okay. Again, oh no, whoopsie. I copied the slide and I forgot that all the animations are on there, but you can see this again. So this is the classical shadow protocol, and my plan was to code that now, but we will not have time for that, and that's okay. I think we don't need to code. It was just a fun little thing that we could do. But I would say then we wrap up. And again, on this pad, you can find, if you're really interested about what would we have done, there's something called tutorial result, I think. And I did everything in there, what we would have done together. So if you're curious, then you can open that. Yes, good. Because now we did not do the coding, I will show you what I coded a long time ago, namely a live updated classical shadow protocol, not with real data, but with simulated data. And you can see here that every time I get a new shadow, I can estimate all the observables that I want, that my heart desire at once. So here, I know it's a bit hard to read, this is the fidelity of my quantum state. This is the subsystem purities. So in this case, I looked at 2 Bell states that are tensored with each other, so for qubits. So I know that when I trace out my 2 subsystems where 1 Bell state lives in, I will always be pure. But if I trace out some spaces where my both Bell states live in, I will always get mixed. I know it's a bit pixely, but this you can see here. Then we have some ZZ correlators, 2 body ZZ correlators. And here we have some XX correlators. And because I was curious what if I would do quantum state tomography with this? So I would really reconstruct my whole quantum state. then you can see that this is now the density matrix estimation. And I did a eigenvalue decomposition for you. And you can see that it looks bad. It has a lot of negative eigenvalues, meaning that this description here is not a description, not a valid description of a quantum state. But somehow, the values that we look at are going in the right direction, and they are pretty close already to the value that they should estimate. I drew the values that they should estimate in slash lines. Even though this is a completely unphysical state, and my density matrix really does not resemble the one that it should resemble. And I found it super cool. Like, you can see that it already converges without the physicality constraint, without having to estimate all these probabilities, which is very costly. And it works. Now, what do I mean with it works? Because how do we know that we actually converged? Because here I can, for example, see that the fidelity, it was at 1, but then it went down again a little bit. Like, how do I know in a real experiment where I don't know the fidelity, where I don't know my correlators, how do I know that I converged? And this will be the topic of the next lecture, calculating sample complexities and giving upper bounds on probabilities that giving upper bounds on the probability that I'm epsilon far away from my actual true value. Okay, and with that, I want to thank you for your attention.